Modern-day weather radar consists of a dish that emits extremely short bursts of microwave radiation called pulses, with slightly longer periods in between in which the radar listens for energy returned to the dish. The pulses emanate outward as waves in a narrow beam, and as the beam comes into contact with objects, both meteorological, like rain and hail, and non-meteorological, like birds and leaves, the radiation is scattered in all directions with only a fraction of it bouncing directly back to the dish. The radar observes this backscattered energy during the listening periods in between pulses, and by recording the time it takes the pulse to leave the antenna, strike the target, and return to the antenna, the radar can calculate how far the target is from the dish. The amount of backscattered energy received by the radar is related to the intensity of the targets. Each pulse has a specific phase, which is essentially how far along in its cycle a wave has progressed at a given time. A wave's phase is influenced by its geometry, wavelength, frequency, amplitude, etc. The difference in phase, also called a phase shift, between a transmitted pulse and the energy scattered back to the radar directly correlates to the velocity of the objects, with a greater phase shift representing greater velocity. These phase shifts comprise the Doppler effect, hence why modern weather radars are Doppler radars.
Storm chasing is hard. Get expert help from a live coach. Discord community link in description.
The number of pulses a radar transmits per second is called the pulse repetition frequency, or PRF. The PRF influences a couple of important quantities called the maximum unambiguous range, or RMAX, and maximum unambiguous velocity, or VMAX. If a radar emits a pulse before the backscattered energy from the previous pulse is received, the radar will be unable to properly determine the range of the target. In other words, the range of the target that the radar measures becomes ambiguous. The maximum unambiguous range is the maximum range from which a transmitted radar pulse can be scattered and received before the next pulse is transmitted. Increasing the PRF decreases the maximum unambiguous range, and vice versa. A radar also has a limit on how much of a phase shift it can detect. If a target is moving so fast that it exceeds the amount of phase shift the radar can detect, its velocity will become ambiguous, meaning that the radar may think that it's stationary or moving the opposite direction at a much different velocity than what it actually is. The maximum unambiguous velocity dictates the maximum range of velocities that can be observed without this ambiguity. We're going to talk more about this later on in this module, but for now, know that as the PRF increases, so does the maximum unambiguous velocity. This creates a dilemma. Increasing the PRF allows us to have a greater breadth of unambiguous velocities, but it would also degrade the maximum unambiguous range, leading to a lot of unreadable data. Decreasing the PRF would give us a much better maximum unambiguous range, but also an increased collection of ambiguous velocities, again leading to erroneous data. Thankfully, radars can operate with an abundance of scanning strategies called volume coverage patterns, or VCPs, to combat this based on the phenomena that are expected within a radar's range. As we know, a radar dish is not stationary, rather it rotates and tilts upward as each full rotation is completed so that we can get a full 360-degree look at what's going on in the lower atmosphere. The full extent, both horizontally and vertically, that a radar scans in one cycle is called a volume. A volume is made up of data at several different elevation angles, also called tilts. When the weather is quiet, the radar can operate in clear air mode, in which it rotates more slowly and scans fewer elevation angles. However, when precipitation is detected, it switches to precipitation mode, which scans more elevation angles more quickly, making it ideal for monitoring rapidly changing severe weather. The wavelength of the pulses a radar emits is also a critical piece of the puzzle. Radars that use shorter wavelength pulses tend to detect smaller particles, meaning higher spatial resolution and more detailed data. However, these particles partially absorb some of this smaller wavelength radiation, a process called attenuation, which leads to degraded data quality the more particles the beam encounters as it goes outward from the dish. Radars are divided into several different bands based on their pulse wavelength. WSR-88Ds, which are National Weather Service radars here in the US, operate at S-band with a wavelength of 8 to 15 centimeters. This is relatively large, making it a good choice for both close range and distant weather observation without significant impacts from attenuation. Terminal Doppler weather radars, or TDWRs, which are found at airports, are C-band radars which use a 4 to 8 centimeter wavelength. This increases spatial resolution but also makes them more susceptible to attenuation. As a result, they are better suited for short-range weather observation. Many mobile radars, like Doppler on wheels, operate with even smaller wavelengths at X-band, which yields extremely high-resolution, close-range data, but frequent issues with attenuation. Alright, now that we've introduced some of the basics of weather radar, let's dive into an overview of the data that radars output. Perhaps the most widely recognized radar product is reflectivity, which is the amount of energy that returns to the radar after scattering back from a target. Reflectivity tells us where precipitation is occurring and how intense that precipitation is, and it's measured in decibels, or dBz, where z is the meteorological variable for reflectivity. In general, the higher the reflectivity, the heavier the precipitation. Reflectivity values below 40 dBz typically indicate light precipitation, while values above 60 to 65 dBz generally represent extremely heavy precipitation, sometimes including hail. These guidelines can vary based on the size of the raindrops. Small drop sizes, like those in tropical systems, return less energy to the radar and, therefore, yield lower reflectivity values than the larger drops of a typical thunderstorm, despite equally torrential rainfall. As we discussed earlier, Doppler radars also measure the phase shift between an emitted pulse and the energy scattered back to the radar to estimate velocity. A target's velocity is comprised of the speed and direction of the target. Negative velocities, which are illustrated as greens, blues, and pinks on typical radar programs, represent targets that are moving toward the radar. These are also called inbound velocities. On the other hand, positive velocities, your reds, oranges, and browns, represent targets that are moving away from the radar. These are outbound velocities. Velocities near zero show up as gray. Depending on the radar program you're using, velocity is measured in either knots or miles per hour. Typically, higher velocity values indicate targets moving more quickly, but, as we mentioned earlier, this depends on the radar's maximum unambiguous velocity. Again, we'll get into this in depth later on in this module. The velocity of a target that you see on a radar program will almost always be slightly less than the actual velocity of the target because radars are at fixed locations, meaning that they can only measure how fast a target is moving toward or away from the radar itself. This is called radial velocity. Every azimuth angle, which is the radar beam's angle from due north, is associated with a radial. Radial velocity is equal to the actual velocity of the target only when the target's motion is directly toward or away from the radar. In other words, directly along a radial. Therefore, the greater the angle between the radar beam and the target's motion, the less the portion of the target's actual velocity that will be sampled, and the less the radial velocity will be. If a target is moving perfectly perpendicular to the radar beam, its radial velocity will be zero. In addition, standard radial velocity, which I'll refer to as just velocity or base velocity from here on out, is the target's velocity relative to the ground. However, storms and their small-scale phenomena, like tornadoes, move with respect to the ground, which can make it difficult to obtain proper velocity measurements. For example, if a storm has 40-mile-per-hour winds and is moving directly at the radar at 30 miles per hour, the radar will output an erroneous base velocity of 70 miles per hour. To combat this, we can use a product called storm relative velocity, which subtracts out the storm motion. This can make it much easier to discern areas of rotation within the broader wind field. Reflectivity and velocity are the two foundational products of weather radar and can tell us a number of things about a storm's behavior and characteristics. However, they only give us a two-dimensional look at targets. Before the early 2010s, WSR-88D radars could only produce reflectivity and velocity measurements, but starting in 2012, the entire network was upgraded to have dual polarization capabilities. Let me explain. The pulses of energy emitted by a radar oscillate in a specific plane, much like the ripples in a calm pond after you toss a pebble into the water. The orientation of the waves is a property called polarization. Prior to the upgrade, radars could only send out pulses that were oriented horizontally, in other words, horizontally polarized. Today, WSR-88D radars send out pulses that are polarized in both the horizontal and vertical, which allows us to obtain vital information about the size, shape, and orientation of targets rather than just their intensity and velocity. Dual polarization yields a few additional products that can be extremely helpful, especially in severe weather situations. The first is called correlation coefficient, shortened to CC or ρHV. Correlation coefficient compares the consistency between backscattered power in the horizontal and vertical planes. In simple terms, it tells us how similar or correlated the targets are that the radar samples. Correlation coefficient is unitless and ranges from 0 to 1. If targets have similar shapes and sizes, the correlation coefficient will be close to 1, but if their shapes and sizes are quite varied, correlation coefficient will decrease. For example, if a storm or a portion of a storm consists of only raindrops, the associated correlation coefficient will be near 1, as all the targets are quite similar to one another. However, if a storm consists of a mix of raindrops and large hail, the correlation coefficient may decrease given reduced consistency among the targets. Correlation coefficient is also a good discriminator between meteorological and non-meteorological targets, with most non-meteorological targets registering a CC value below 0.9. The exception is large wet hail and large wet snowflakes, which typically yield CC values between 0.8 and 0.97. The next dual polarization product of note is differential reflectivity, or ZDR, which is essentially the ratio of the backscattered energy in the horizontal plane to the backscattered energy in the vertical plane. After a bit of mathematical cleanup, we get a range of possible ZDR values between positive and negative 7.9 decibels. Differential reflectivity gives us valuable insight into the orientation of targets being sampled. ZDR values near 0 mean that the backscattered energy was similar between the horizontal and vertical planes, indicating more spherical targets like small raindrops or hail. Highly positive ZDR values suggest that targets are much wider than they are tall, such as large raindrops that flatten out as they fall. The opposite is true for highly negative ZDR values. They indicate targets that are much taller than they are wide, such as falling ice crystals or elongated snowflakes. Highly negative ZDR values are quite rare in severe weather situations. The final dual polarization product we'll discuss is specific differential phase, or KDP. KDP is derived from a similar product called differential phase shift, or FDP. In essence, FDP is a measure of attenuation in the horizontal and vertical planes. It can be a bit cumbersome to analyze, so KDP is much more commonly used instead. KDP shows the gradient of FDP, in other words, how phase shift and, in turn, attenuation changes in the horizontal and vertical over a given distance along a radial. Since phase shift is measured in degrees, KDP has units of degrees per kilometer and ranges from -2 to 10. Increasing values of KDP represent an increase in the size and concentration of raindrops, which can attenuate the radar beam more. This suggests heavier rainfall. KDP may vary between areas of precipitation, even if reflectivity among these areas is similar.
Remember to check out those links in the description below, and then watch another video.